Hey everybody, it's Miss A again. I want everyone to keep in mind that we're going to have an awesome week this week because this coming weekend is Memorial Day weekend and hopefully some nice warm weather. So keep your spirits up. We don't have much longer of this craziness left. And this week, we're going to be talking about some interesting stuff. We're going to be identifying and calculating exponential growth and decay. So, for those of you who really like money, exponential growth is definitely something that you guys might want to look into. Different types of bank accounts that you can get can provide you with some exponential growth of your money in your bank account, which is pretty cool. This week's video is being broken down into 4 parts. I'm going to come back to this after every section to let you know what Delta Math connects with the part of the video. And stay tuned for video 2 this week. It's going to be exciting. So before we get started, I do want to let you guys know a calculator and a highlighter are definitely going to be needed. So if you guys have a graphing calculator or a calculator at least that shows you 2 lines within the screen, I would say that those calculators are the best for this situation just because you will be entering in a lot. If not, no worries. If you go onto Desmos and you click on their scientific calculator or go to desmos.com/scientific, you will see a calculator that looks like this on your screen. And the reason that I love this calculator so much and that I am going to encourage everyone to use it no matter what, is that you have these really awesome function buttons here where you can use a fraction button, you can use an exponent button, and you can type in something this crazy. Yes, this is one of the problems that we're going to do. Don't worry though, it's a formula, so don't freak out. It's super simple, but you can type all of this into the calculator at once and see your answer right here. So you don't have to worry about the order of operations so much, but I will remind you of them as we go. So I'll come back to this later when we need it, but having a calculator handy is definitely going to be really important. So let's get started. Part 1. All right, in part 1 of this video, we're just going to talk about some simple exponential growth and decay. So the picture that you're seeing here is an example of one function that is considered to show exponential growth, and then you have a second function that is showing you exponential decay. As you guys can see, exponential growth, this is something that might look familiar to you with all the coronavirus information going on right now. We're talking about flattening the curve because what they're hoping to have happen is that it goes like this and it kind of plateaus and then starts to drop off, looking more like a bell curve. But this is what coronavirus essentially looked like from the start, just crazy numbers of more and more people getting it. This is something that you would like to see your bank account represented by. This is something you don't want to see your bank account represented by, exponential decay. This is more for your science classes. When they are talking about decay from radioactive isotopes and stuff like that. Or sometimes it can actually be considered in situations where you're looking at when something depreciates in value. Like a lot of us are probably familiar with cars, how they over time are not worth as much as when you first purchased them. So here is your first formula that you're going to be looking at. This is just ordinary exponential growth and decay. It's usually a situation where you're talking about that over the course of 1 year, there's a specific rate that you will be either increasing or decreasing by. And I'll show you what I mean by that. This A over here stands for your total amount or your amount over time, depending on what teacher you have, what textbook you are reading, and also what YouTube video you're watching. Some people might refer to it as 2 different things. A sub 0. This is not A times 0. This is not an O. This is A sub 0. It's kind of like an exponent, but it's written down low. It means initial amount. This is whatever your starting value is. Then you've got 1 plus R. R represents a rate. It's always going to be given to you as a percent. You're going to need to turn it into a decimal before you plug it in. And T is going to represent some form of time. Now, this number here, whatever 1 plus your rate is, if that number comes out to be larger than 1, it's going to represent growth, exponential growth, and it's going to be considered your growth factor. If when you add those two numbers together, you get a number that is less than 1, you're going to be looking at some exponential decay, and this will be referred to as your decay factor. So for right now, just to get our feet wet, we're only going to be focusing on this growth or decay factor and determining what the situation is representing. Just so you know, guys, I also did create a clean copy of these notes, especially since we're working with word problems. I put them on Google Classroom, and if you are not technically my student, I did make them available to your teachers. All right, so ordinary growth and decay, again, this is occurring once per year. We're going to take a look at this and determine what's what. So given the following exponential function, identify the change that represents growth or decay and determine the percent rate of increase or decrease. So honestly, we don't need to know what the situation represents. If it's money, if it's a population of people, if it's the value of a car, whatever the case might be, we don't need to know. All we need to look at is this guy right here. And I've written our formula across the top so it's a little easier to identify kind of what's what and line it up. But this number right here, okay, 1.19. 1.19, how does that compare to 1? Is that larger or smaller than 1? If you said larger, you are correct. So that means that this is representing growth. If it's representing growth, we want to now identify the rate because that's what it was asking us to do. First, to identify if it's growth or decay, which we did. Now we need to identify the rate. So 1 plus some number gave us 1.19. If you guys need to grab your calculators now and subtract this over to find out what's left, this number right here is going to be 0.19. And that means that this represents our actual rate. 1 plus our rate, right, is going to give us that number on the inside. So if this is our rate, that's our rate in the decimal version. So if we move it over twice, we will get 19% increase. Let's be technical here since we're talking about growth. A 19% increase to represent growth. Let's look at a second example. Again, same directions here. Given the following exponential function, identify whether the change represents growth or decay, and then determine the percent rate of increase or decrease. So again, doesn't matter what the situation represents. All we care about is this number inside here. We need to find out if it is a growth or decay factor. So we are going to compare 0.971 to the number 1. Is that larger or smaller? Very good. It is smaller, so that means that this represents a situation of exponential decay. So with that being said, 1 plus some number gave us 0.971. So again, if you need your calculators, subtract this over. If you notice, you are taking a smaller number and subtracting a larger number, so that means that you should get a negative number here. So don't freak out. It is negative 0.029. That's okay. This negative is confirming that we are decaying. So that's all you need to know. If it is decaying, then you're going to be subtracting that rate because it's taking away value. It's not adding value. So this is just a confirmation of what we had originally said. We do need to turn this into its percent value instead of its decimal value. So we're going to move this over twice, and we're getting 2.9% decrease. There you go. So again, when you are increasing or growing, you're going to add your rate as a decimal. And when you are decaying, you are going to be subtracting your rate as a decimal. So this concludes part 1 of our video. If you're ready to go, you guys can go on into Delta Math and click on Find Growth Decay Percentage Level 1 so that you can continue to work on problems that are just like that. All right, part 2. So in part 2 of this video, we are going to be calculating that yearly growth or decay. Just like we were doing before, by looking at the problems in part one, we are going to actually be plugging in these numbers and coming up with a final answer. So let's take a look at our first problem. All right, $4,800. I'm going to use my highlighter. So if you didn't grab a highlighter, go ahead and click pause real quick. $4,800 is placed into an account with an annual interest rate. So annual is going to be another important word to us so that we know what formula to use. We only know one so far. Annual interest rate of 6.5%. How much will be in the account after 14 years? Round your answer to the nearest cent. All right. So we're going to be using this formula, and I like to highlight the important information and then list it out here to make it a little easier to plug in. So $4,800 represents the initial amount that we placed into this bank account. So I'm going to list that out, as my initial amount. Our next number that we came across was our rate of 6.5%. So if I turn that into a decimal, it is 0.065. Since we are talking about money in a bank account gaining interest, we're going to add this rate. So I like to just put a little plus to remind myself of that. And then it says how much will be in the account after 14 years. 14 years is our time. And we're going to round to the nearest cent. So it looks like we have all the variables that we need. So let's go ahead and plug in. So this is going to look like 4,800 times 1 plus 0.065 to the power of 14. Again, this is where that calculator is going to come in handy. So if you don't have it with you, please press pause and go grab it, or go onto Delta Math, because you can type in exactly what we wrote out right in here and it will give you your answer right away. You can type it in right as you see it. When you do type this into your calculator, again, when you're using exponents, you could use a little caret and then make sure you put your exponents in parentheses so that your calculator doesn't go cuckoo crazy on you. This is what you should be seeing on your calculator screen, 11,591, and then we've got some numbers after that decimal point, and we're going to round to the nearest cent, which means that we're going to be looking here, which is going to tell us to round up from 39 to 40. So we are going to have a final answer of $11,591.40 in that bank account after not touching it for 14 years. It's pretty nice that you can almost triple your money in that amount of time without adding anything to it. All right, let's try another one. Again, your highlighter is going to be handy. So we have a town population of 5,000. It grows. That's letting me know that it's increasing, right? At 2% every year. What will be the population after 5 years to the nearest whole number? Now, of course, we're dealing with people here, so we're not going to be talking about a fraction of a person. So let's list out what we have. 5,000 is the initial population, so that's my A sub 0. It grows at a rate of 2%, so that's my rate. And if I turn 2% into a decimal, that is 0.02. My next number was 5 years, so that's time. And all we have to do now is plug in because we have all of our values here. So it's going to look like 5,000 times 1 plus, because remember it said it was growing, right? So plus 0.02 to the power of 5. Again, if you just plug all of this into your calculator, you should be seeing on your calculator screen 5,520 point, and you've got a couple of numbers here after your decimal. They want us to round to the nearest whole number. 0.4 is not enough to round up, so we are going to say a final answer of 5,520 people are going to be living in this town. All right. All right, last example. So we've got an element that has a mass of 230 grams. It is decaying. All right, so I've got to switch it up this time by 27.7% every minute. How much of this element is remaining after 8 minutes? We're going to round to the nearest tenth of a gram. All right, so let's list out everything we have. 230 is the initial amount of this radioactive substance that I have, this element, sorry, that I have. It says it's decaying by 27.7%, so that's our rate. So 27.7%, when I turn that into a decimal, is 0.277. It's decaying, so I'm going to put a big old minus sign here to remind myself of that, because when I decay, I'm going to take away value, so I'm going to subtract it. Then we've got how much is remaining after 8 minutes, so that's our time, and we can go ahead and plug in because that's everything. So we've got 230 times 1 minus 0.277 all to the power of 8. Again, type all this into your calculator. You're going to have 17 point, and we've got a couple of numbers here after this decimal. All right. Does keep going, but we are rounding to the nearest tenth, so we're going to look here, which means that we are going to round up. Final answer of 17.2 grams of this element. All right. Now, just so that you guys know, as like a little side note on this, if you do look at an example problem or for help within Delta Math, you will see that they write out their initial equation like this, but don't worry, that's the same as the equation that we're using, because look, after they plug everything in, it looks exactly the same. Here's the initial value, here's 1 plus the rate, all raised to an exponent of time. They just are using different variables and a slightly different setup, but it is the same. Don't let your eyes play a trick on you, all right? All right, so this concludes part 2 of our video for this week. So if you guys are ready to just do some simple growth and decay problems, you can go ahead into Delta Math and click on Exponential Functions Basic. All right, part 3. Part 3 is a little bit more complicated. We're going to be talking about bank accounts most of the time. We're going to be talking about money because we're going to be talking about compound interest. And there are 2 different types of compound interest. There's compound interest that happens n number of times per year. So this is going to be multiple times per year, not once. The original formula from part 1 of this video is when it happens once per year. This is going to be a situation where your interest is calculated multiple times per year. So again, A still stands for our total amount. P is now taking the place of that A sub 0. It stands for principal. The reason we change this is because when we're talking about initial amount of money that you're investing, that specific vocabulary term is principal, okay? So it's the original amount of money that you invested, but it's the same thing as A sub 0. Times 1 plus, we've got R, which is representing our rate. Again, they're going to give you the percent. You type in the decimal over N, and you're going to see this N pop up over here in the exponent again. These N's both mean the same thing. So yes, the same number gets plugged in twice to these 2 spots. It is the number of times per year that your rate is being, your interest is being compounded. So you're going to see things like daily. Well, we have 365 days in the year, so 365 is going to go in for that N. You're going to see terms like monthly. We have 12 months, so we've got N is 12. Quarterly, that means when you split the year into 4 time segments, so you've got 4 for that N. Semi-annually, some of you know this from shopping, semi-annual sale, usually it happens twice a year, so 2 would go in for that N. So whatever that number of times per year, that's what's going in for that N. And then T is just time in general. They're going to be talking about number of times per year for so many years. So if I said our interest was being compounded monthly, 12, for 10 years, 10. Okay, so that's the difference between the N and the T. A little bit confusing there. Our other formula that we're going to be using uses this number E. I will give you guys a link so that you can look up a little bit more about this if you're interested, but just for the sake of time for this video, I'm just going to kind of wrap this up in a nutshell. You guys have probably heard of Leonhard Euler before. He's the father of geometry. He's a really cool guy. But basically, back in the day when, you know, people were bored and they were interested in math. They weren't sitting around watching Netflix and chilling. They were doing some research. And Leonard said, you know what? I'm looking at this formula here, and I'm going to constantly make this number here larger and larger and larger and larger. You guys can try this. You can enter in like 10, 100, 1,000, 1 million into these two spots here and see what happens. But I can already tell you what happens because Leonhard Euler was nice enough to do it thousands and thousands of times over and prove this for us, to say that this value will get closer and closer to this number, 2.71828. And this is now known as the value of E. So this is all represented with the letter E. So E is a natural base. We're going to talk about this more in logs next week, but it's a natural base, and it's kind of like pi, right? Pi is a symbol, but it is also a value, 3.14. We also have E. It's a symbol, but it's also a value, 2.71828. And it does keep going. So again, just to give you a little bit of history on this, here is E representing its exponential growth and decay here. Positive exponent gives you the exponential growth. The negative exponent gives you the exponential decay, just so that you guys have a little bit of a visual. But otherwise, I would like to introduce you to PERT. PERT is your new friend, all right? PERT is used when you continuously compound interest. So literally, it is constantly happening. It's not only happening 12 times a year or 4 times a year. It's happening all the time. Again, A is still standing for the same thing, your total amount. P is still standing for the same thing, it's principal, the amount of money that you originally invest. E, this is a button on your calculator, okay? If you type in the letter E on your keyboard into Desmos, if you're using this calculator, it will show up as the number. It is smart enough to recognize that. R is still your rate. It's given to you as a percent. You type it in as a decimal, and T is still standing for time. So we will know the difference between these two formulas based on what the problem is telling us. Are we continuously compounding our interest, or are we compounding our interest so many times per year? That's how you're going to know whether to use the crazy formula or PERT, our new best friend. All right, so let's go ahead and get started here. So in this section for Delta Math, you've got your 3 different situations to choose from. So I suggest writing these guys at the top of your note page, or just maybe on a flashcard or something, and keeping it handy. So if the question is asking you to find an amount annually or just after so many years, and the percent is being talked about at an annual rate, you're going to be using our original formula from part 1. If you're compounding the interest continuously, PERT is going to be your new best friend. N number of times per year, we've got the cuckoo crazy formula here. So let's get started and take a look. Your highlighter is going to come in handy. So Lucy is going to invest $19,000 into an account that pays an interest rate of 3% compounded annually. All right, so that means that I'm going to be using this guy here. Assuming no deposits or withdrawals are made, so we don't touch the account, how much money to the nearest $100, we're going to have to round here, would be in the account after 8 years? So let's write down what we've got. So we've got $19,000. So that's the original amount of money that we're going to invest. Okay, we've got 3%, that's our rate, and if we change 3% into its decimal form, then we've got 0.03, and it's interest on money, so we're going to be adding this interest. And then we've got 8 years, which is our time, so we can go ahead and plug in. So we've got 19,000 times 1 plus our rate, because we are gaining interest on this money for 8 years. You can plug this right into your calculator. Again, type it right into the Desmos Scientific Calculator. As you can see, the crazy cuckoo formula, it's just fine. It handles it just fine, which is really nice. Otherwise, do remember that you want to put your exponents first before multiplication, or to put your exponents caret and then put them in parentheses when putting them into the calculator. Anyway, what should pop up on your calculator screen is Uh-oh, I made a boo-boo here. I made a boo-boo in my calculations, guys. 1 second. I'm going to type this one in with you. All right. Going a little off script here. 19. I think I missed a 0 the first time I plugged this in. Now that I'm looking at my work. To the 8th power. Aha! There we go. Okay. Now this is better. So you should see on your calculator screen $24,068, and then you've got a couple numbers after that decimal point. All right, good thing I had my calculator handy. They're asking us to round to nearest $100. So $100 is here. So we're going to look over at this spot, and it's telling me 6 is enough to round up. So our final answer is going to be $24,100. Okay, so the 100 spot, I know that's a little bit weird. They're just asking for a roundabout. You know, you would be talking maybe to somebody and say, oh, you know, it's just about $24,100. You wouldn't necessarily go into the cents if you're just predicting a roundabout value. All right, situation number 2, we're going to help out Zoe. Zoe is investing $230 into an account that's paying an interest rate of 6.3%, and it's being compounded daily. All right, so that means I'm going to be using that cuckoo crazy formula because it's being compounded a certain number of times per year, right? Assuming no deposits or withdrawals are made, so we don't touch the account, how much money to the nearest $100, we're going to round, would be in the account after 12 years. So let's go ahead and write everything down that we need here. So $230 is the initial amount that she's putting in the account. So remember, that's your principal. We've got a rate of 6.3%. So if we turn that into its decimal form, we're going to have 0.063. It's compounded daily, so that is our N number of times daily, 365 days per year. And then for 12 years, that's our time. So now we can go ahead and plug this all in. So our total amount is going to be $230 times 1 plus our rate, which is 0.063, over the number of times per year, 365, to the power of, again, number of times per year, right? So 365 times the amount of time that we want to leave all this money in the account, which is that 12 years we want to leave it in there for. So again, take a look. Desmos Scientific Calculator is pretty awesome. It can handle all of this, right? So take a look at that. $489 and some change will be in there. So let me write that down after you type this into your calculator. All right. So when you type that all in, it says round to nearest 100. So we're going to be looking at the 100 spot. 8 is enough to say to go up. So we're just going to say it's roughly $500 after we round. All right. In our last example, Parker. Parker is investing $7,800 in an account paying an interest rate of 1.7%, and it's going to be compounded continuously. So compounding continuously, that's my friend Pert. Assuming no deposits or withdrawals are made, so we don't touch the account, how much money to the nearest dollar, that's what we're going to be rounding to, would be in the account after 11 years. So let's go ahead and write down everything we have. $7,800 is the initial amount that he invests, so that's going to be our principal. 1.7% is our rate, and we need to change that into its decimal form, so 0.017. It's compounded continuously, so that's PERT, and we're going to be leaving it in there for 11 years, so that's our time. That's all we need, because remember, E is not a variable that we plug in for. It's a number. When you hit the E button on your calculator, or when you type in E to the Desmos calculator, it does know to use that numerical value. So here we go. We've got 7,800 E to the 0.017 times 11. Again, type it all in at once. Let the calculator do the work. You should get 9,403 and some change. All right, it says round to the nearest dollar, so whole dollar here. That 8 is enough to tell us to go up. So our total amount is going to be 9,404 $4. All right. This concludes part 3 of our video. So if you're good to go, you can go ahead and go into Delta Math and click on compounding, solving for a future value. I would suggest breaking that up over 2 days because like I said, there are 3 formulas, so it might take you a little bit longer to get through this. All right, last part. My apologies for this video being a little bit longer than usual. All right, but I'm trying my best to get through this in a reasonable amount of time without rushing. So again, if you feel a little rushed, feel free to pause, rewind, listen to me again, or even shoot me an email. I can definitely help you out or make you another short video on something with another explanation. This last part is about half-life and doubling time. A lot of times, half-life especially is talked about in your science classes. It's representing decay. Usually they're talking about over the amount of time, a specific amount of time, half of something disappears, okay? Some of you might be familiar with Mr. Tucker's Twinkie or his Oreos that were sitting in the back of his classroom for like 15 years untouched, and they like literally weren't decaying, and it was absolutely disgusting. Well, we're literally talking about that. If you leave something to decay, to just totally rot and disappear and go back into the earth, how long does it take for half of that substance to disappear? So you've got A is your total amount, A sub 0 is your initial amount, half is representing your half-life, so that's always half, it's never changed. T still represents time, but the other confusing part of this is there is another unit of time. It's H. This is how long your half-life is. So H stands for half-life. So they will tell you, let's say the half-life takes 30 days, right? And then they want to know how much will be there after 90 days. So 30 days is how long it takes for half-life to occur. I want to know how much is there after 90 days. So this is what I want to know. Doubling time is similar in its concept, but instead of being cut in half, you're going to double in your growth. So it represents growth. So this is still your total amount, your initial amount. 2 is representing the doubling that's going on. So this will never change. It will always be a 2. And then again, you've got your 2 different units of time for your exponent. T is the time that you want to know. D represents the doubling amount. So let's say that it takes 2 weeks time for something to double, and I want to know after 10 weeks how much is there. So 2 weeks for doubling time, 10 weeks for how much I want to know. That's the difference between those 2 values right there. All right, so let's go ahead and take a look. We're almost done. All right, half-life and doubling time. Again, I suggest writing out these 2 formulas and having them nearby. And your trusty highlighter. So element X is a radioactive isotope such that every 27 years, its mass decreases. Okay, so already I know that I'm going to be dealing with half-life because I'm decreasing. But it says decreases by half. So that's half-life. Given that the initial mass of a sample of element X is 7,900 grams, how much of the element would remain after 12 years? We're going to round to the nearest whole number. All right, so let's now write down what we have here. So 27 years, it decreases by half. So that is the half-life. So that's our H is 27. The initial mass is 7,900. So that's A sub 0. How much will remain after 12 years? That's the time that we want to know. And we have to round. So we now know everything that we need to plug in. So let's go ahead and do that. 7,900 times 1/2. Again, remember that half is standard for half-life. To the power of 12 over 27. Again, you can put this into your calculators. If you are using a regular old calculator, then you need to put the 1/2 in parentheses. You can certainly just put in a 0.5 if that's easier to type in. Put a caret to the power of. You need to put this in parentheses. Your calculator will make a boo-boo. If you like, the Desmos calculator does have that fraction button, so you can just hit the fraction button when you're up here and it will do that for you. No worries. But when you type this into your calculator, you should be seeing 5,805, and then we've got a few numbers after that decimal. It says it wants us to round to the nearest whole number, so we're going to be looking here. 4 is not enough to round up, so we've got 5,805 grams, which makes sense because it should be less than the original since we're decaying. All right, example number 2. In a lab experiment, 3,500 bacteria are placed into a petri dish. The conditions are such that the number of bacteria is able to double every 19 hours. Okay, so doubling time is what I'm going to use. How many bacteria are going to be there after 21 hours? Round to the nearest whole number. So let's write down what we have. 3,500 bacteria is the initial amount of bacteria that I started this experiment with. Doubling time is 19 hours, so that's D. I'm going to leave it there for 21 hours, so that's the time that I want to know. And now we can go ahead and plug in. So our total amount is going to be 3,500 times 2, because that represents the doubling time, to the power of 21 over 19. Type this into your calculator. We should see 7,529, and then we've got a couple of numbers after that decimal point. It says round to the nearest whole number. That 8 is enough to tell us to go up, but since this is a 9, 29 is going to round up to 30. So we've got 7,530 bacteria, which makes sense because we are increasing, we are growing, and it's more than the original amount. All right, let's do one more of each and then we'll call it quits for the week. All right, element X is a radioactive isotope such that every 90 years, wow, that's a long time, its mass decreases by half. So this is half-life. Given that the initial mass of a sample X is 30 grams, how much of the element would remain after 12 years? Round to the nearest whole number. All right, let's write down what we have then. So every 90 years we decrease by half, so that is our half-life. The initial mass is 30 grams, so that's our A sub 0. We're going to leave it there for 12 years, so that's the time that I want to know. And we're going to round to the nearest whole number, so let's go ahead and plug in. So we've got 30 times 1/2 for half-life to the power of 12 over 90. Type that into your calculator. You've got 82.055023. We're going to round to nearest whole number, so that's here. 0 is not enough to tell us to go up. So we've got 82 grams, which again makes sense because we are, wait. I made a mistake here. Oh gosh. Hold on one second. I am so sorry, guys. What did I do? I typed in another boo-boo. If anyone caught me there, you see how I was able to catch myself? I'm so glad that I made this mistake. That number came out to 82, which is larger than 30, which makes no sense because if it is decreasing, it should be smaller than 30. So let's actually type this in together. We've got 30 times 1/2 to the 12 over 90. Aha, that's better. All right, 27.3516, and it keeps going. We're rounding to the nearest whole. 3 is not enough to tell us to go up, so we've got final answer of 27 grams. Much, much better. All right, and that makes sense because, again, I was decreasing. All right, last one. All right, in a lab experiment, 80 bacteria are placed into a petri dish. The conditions are such that the number of bacteria is able to double every 19 hours. So I'm using my doubling formula. How many bacteria would be there after 17 hours? Round to the nearest whole. All right, so let's go ahead and do this. 80 bacteria are the original amount. Doubling every 19 hours, so that's my doubling time. We're going to leave it there for 17 hours, so that's the time that I want to know. So let's go ahead and plug this all in. So we've got 80 times 2 for doubling to the power of 17 over 19. All right, put that into your calculator. We're going to get 148.74165. We're rounding to the nearest whole. 7 tells my 8 to go up. So we've got a final answer of 149 bacteria, which makes sense because, again, we are showing exponential growth here. All right, this concludes part 4 of our video. Again, sorry for the length, guys, but I want to make sure, especially with word problems, we're good to go. If you guys feel comfortable, go ahead and click on half-life and doubling time in Delta Math. And stay tuned, guys. Video 2 certainly going to be worth it. I've got something fun for video 2 this week, all right? So see you guys later.